Okay. So yes, thank you. I'm Mariaveronica de Angelis. I'm talking about dynamics of quantum anisotropies in a Taub universe in the WKB approximation. So one of the most interesting open questions in theoretical cosmology concern how a primordial quantum universe reaches a classical isotropic limit. So the aim of the work is to study an homogeneous and anisotropic cosmological model, that is the Taub universe, in the presence of a cosmological constant and a free scalar, minimally coupled scalar field, because these two last ingredients well mimic the slow rolling phase of an inflationary scenario. So then also the analysis of the dynamics is performed in a semi-classical picture to give interpretation to the anisotropy wave function. So we will study the dynamical evolution of the quantum anisotropies during the inflation phase, then its classical behavior, and then we will use a classical field as a quantum variable and not a classical one. So a Taub model is a homogeneous universe, is anisotropic, so it has a different evolution of a scale factor from the other two, and the space-time is described by this kind of line element, in which omega A are the the left invariant one forms, and beta is the matrix that contains the gravitational degrees of freedom. So in this case, the anisotropy. And there is just one anisotropy, is beta plus. The other one, beta minus, is equal to 0. Otherwise, it will be, for beta minus different from 0, we will have Bianchi-9 model. That is another kind of model. So the behavior of a massless scalar field that we added well approximates that one of an inflation field during the slow rolling dynamics, when the potential term is essentially constant and it provides the cosmological term. We know also the potential that derives from the spatial scalar curvature. And then we know that in quantum cosmology, the dynamics is generated by a null scalar constraint h equal to 0. And so an external time definition is absent. So in this perspective, we can consider a small quantum subsystem of the semi-classical universe, and we can write the Wheeler-DeWitt equation in this way, where in which the operator H0 represents the classical Hamiltonian obtained by neglecting the quantum variables and the respective momenta, and HQ is the quantum Hamiltonian. So to justify the smallness of the quantum subspace, Vilenkin imposed the following reasonable assumption. So the ratio between the two Hamiltonians is of the order of h bar, and we can write again the wave function. So we can divide it in a semi-classical part and in a quantum part. So we can put these in the Wheeler-DeWitt equation, and in such a way, the Wheeler-DeWitt can be decomposed in three equations in order of h bar. And in the lowest order, we obtain the Hamilton-Jacobi for the classical action I. So this is the general equation. And in our case, we have this equation, and this is the result, in which alpha and phi, the scalar field. So alpha is the volume of the universe, and the scalar field is classical. And then in the next order, we have the continuity equation for the amplitude A. So this is our case. And then we have the Schrodinger equation. So the Schrodinger equation we find for the subsystem in the background allows to define a dynamical evolution for the quantum subspace. So there is a division of the mini superspace variables between the volume of the universe and the scalar field taken as a semi-classical variables, and the anisotropy regarded as the quantum one. Moreover, according to the Vilenkin idea of the small quantum subsystem, we consider the quasi-isotropic regime so that the potential term of the Taub model gets a quadratic form. So we have like 24 beta plus squared. Then we know the solution of the time-dependent Schrodinger equation, but that is this. But a non-trivial step in this construction is to obtain an analytical solution for ρ, because we have to solve this PDE where omega is the frequency that for us was a bit ugly. So we used we make use of the Lewis method. So we found H, R, and Brodsky and W, and then alpha, that is the phase space. So this scheme allows us to analyze an evolution of the wave function once assigned a generic initial condition. So now we can analyze the wave packets, so the evolution of the small quantum subsystem, how with the probability density. So we analyze this, and to build a complete probability distribution, we calculate 35 Hermite polynomials. So then, in order to show the time evolution, we compute the wave function at different values of tau. So for tau that tends to 0, we have A, the scale factor, that tends to infinity, so the expansions of the volume of the universe. What we see is that the profile of the Gaussian probability density becomes more and more peaked as the volume of the universe expands during the de Sitter phase. However, the analytical solutions, the analytical behavior we fixed for rho, for the function, rho, suggests that the Gaussian cannot reach a real delta function as indicated in Battisti-Belvedere, while it must emerge a steady, small but finite value of the standard deviation of the anisotropy, the quantum variable. So this behavior is also confirmed by the asymptotic study of an exact Gaussian solution of the time-dependent Schrodinger equation. So as we can see here, sigma. And so again, when the universe expands, the standard deviation exponentially decays to a constant value. So these are quite surprising results, suggest that, as we shall see below, although the anisotropy cannot have the same non-suppressed behavior of the scalar field, in a fully homogeneous scenario, it could originate a smaller tensorial component of the primordial spectrum. And also, on a classical level, the universe anisotropy decays to a constant value, but in this case, it has no physical meaning, since it can be reabsorbed into the definition of the one forms of the Taub model. And the cosmological classical field is responsible for the inflation and has also small inhomogeneities, inhomogeneous quantum fluctuation, and the generation of density inhomogeneities relies just in considering such small quantum corrections during the de-rolling phase as the sources of the perturbation observed today. But since the address model is intrinsically homogeneous, we cannot consider the spatial dependence of the quantum field. Nonetheless, we can study the case in which also the scalar field is a quantum degree of freedom and compare its behavior with that one of the anisotropy. So, moving to the general solution, we get this function. Where is this function? And so this represents a spreading wave packet in phi due to the absence of any potential term that governs its dynamics. And so what we have done, we have found that starting with an isotropic universe, we can reach the quasi-isotropization we can reach the quasi-isotropization, yes, the quasi-isotropization, and treating the volume, its volume as a quasi-classical variable. And the great result is that we found an analytical solution that shows that a small quantum relic survives after the de Sitter phase, and if the universe anisotropy is small enough to be in a quantum regime when inflation starts, it is still there. It's still there in the late universe. In addition, when we consider the scalar field as a quantum degree of freedom, we see that due to the absence of a significant potential governing its dynamics during the slow rolling phase, the packet spreads as the expansion goes by. And this can be considered as a starting point by adding the space dependence, for example, to understand that its fluctuation can survive after inflation. Thank you.
Thank you very much. And I'll open the floor to questions. So Greg Ashton is asking, are there predictions for the observable signatures of the anisotropy in the late universe?
Sorry, Can you repeat that?
Are there predictions for the observable signatures of the anisotropy in the late universe?
Okay, we were thinking about like observables in the cosmic variance, because these tensorial degrees of freedom, I mean, beta plus and beta minus are the directions. So the opposite directions. So maybe we can see something in the CMB, in the cosmic variance. But yeah, that's just the one, maybe the most important thing that we can think about, like observables. But then, yeah, at least.
And do you expect that the results that you obtain to carry over to other types of field as well?
Yes.
Okay. Okay.